1 second. I actually record this one. So for example, if you have a fluid flow problem, what you care about is the velocity field and the pressure field. And sometimes a typical mistake people make is they say what is the velocity input, what's the flow rate output, things like that, but they forget to give a pressure constraint. So then basically it's not a unique solution system. You could have the pressure adding any constant to the entire system and it'll still be the solution. So in that case, COMSOL either cannot give you a converged solution or it'll give you an arbitrary solution. And the better way, a more predictive way of getting a right result is to add a pressure point constraint on one of the points, like a gauge fixing. And then same for the electric problem as well. Actually, if you do have the current, like input current of 1 amp and output current, but you don't give a reference point, then you'll have the same situation. So you do want to constrain just one point. So you can easily do so by right-click and then add a point condition, and then add a ground somewhere in the system or any kind of potential. And sometimes you actually, for example, don't know what is the reference point, but then you know kind of like a floating potential. So we do have other conditions. I'm not too familiar with the AC/DC part of it, but we do have different terminal types, floating potential, and other things you can use. Yeah, but you're very right. So a lot of times in physical world, we think in the very physics intuition kind of way, but in the numerical world, then it's interpreted differently, and you have to think from the mathematical point of view and how the machine actually understands those information. So. Another important point, since you mentioned, is for numerical solutions, so far, can we trust the results? Can we trust that 768, 568? Maybe, but I wouldn't trust it to the digits, because so far we're using a relatively coarse mesh. So in numerical studies, what you always want to do is you can start with a coarse mesh so that it solves faster. And then after you do that, refine the mesh a couple of times, actually, more than a couple of times, and make sure that the solution doesn't change according to the mesh density. Then you know you actually eliminated the numerical artifacts and you're actually looking at the converged solution. Of course, the engineer have different tolerances of errors, so you'll see the asymptotic limits as you refine the mesh, and then you can determine, I'll just use less memory and be happy with that 5% error. So that is your call in terms of how fine eventually you want to mesh the geometry. There would be another approach, which is actually under the solver setting, a more automatic way, which is to add adaptive mesh refinement. So basically what it does is, depending on what error estimate you gave, what tolerance you gave, it'll automatically insert mesh points where necessary. Say where the gradient is high, where you think you'll see a lot of things happening. Then that is going to be more memory intensive, but it's going to be more efficient in terms of determining where to insert the mesh, because otherwise you can do a local refinement in a manual way, which will take you more time in terms of choosing which region to refine and how fine to how many iterations to refine it. So yeah, something that comes in handy. All right, so that's the second physics. We'll go through the third physics really quick by, again, right-click on component 1, add physics. And we are going to choose structural mechanics, solid mechanics interface added to the component. So by now you already know the drill, right? You close the physics panel. You have the solid mechanics here. You have 3 default nodes, a default boundary condition, free to move everywhere, default governing equation of linear elastic material. If you want to change that, add nonlinearity or pre-stress or thermal stress, you do the right click on the material. So in this case, we're going to just add a thermal expansion and say the temperature calculation for thermal expansion comes from the heat transfer physics. And then that's it. So that's how we tied the second physics to the third one. And then the free to deform everywhere, again, that's not enough constraint. Another example actually for constraint is a structural problem. For a 3D structure, who knows how many degrees of freedom there are if it's a rigid body? More or less rigid. 6, that's right, yeah. So how do you have a unique solution? You need 6 constraints. So a typical way is people fix one point that eliminates 3 degrees of freedom. Then the second point, you say you can only move in one direction, so in case the structure actually expands, but it will still stay on the same axis. So that eliminates another 2, and then another rotational one. So on the third point, you say you can only move on this surface. So that's how you eliminate the 6 degrees of freedom. Or you know, if you know that the shape on one end doesn't change, you can actually glue the entire surface to another surface, say a fixed surface. So that'll of course be sufficient for eliminating the uncertainty here. All right, so in this case, we're gonna just use the fixed constraint on the 2 feet. Actually, I could use the drop-down feet that'll assign the same condition that u, which is the vector, x, y, z component of displacement, all equals to 0. I think that's it. So we could move on to the study. So just quickly check, there are 3 physics that will all be solved for. There's more and more green toggles shows up, means those conditions will be used. Those material properties will be used by the 3 different physics. And then we'll just hit compute. Well, so far it's actually a 2-way coupling between physics number 1 and 2, but a 1-way coupling between physics 2 and 3. So what I could have done is in the study step, I can use step 1 to solve for physics 1 and 2, and then step 2 to solve for physics 3, use the information from step 1. So, but in this case, the memory requirement is very minimal. So how am I going to do the visualization for the 3rd physics? I could right-click on the surface plot of the temperature, add a deformation plot, use the deformation to show the XYZ component deformation. So you see what's the straight line, the initial shape, and the shaded part after deformation is actually exaggerated by 53 times. I can change that to 1. So you have a very small gap between the initial shape and the after deformation shape. Of course, you can exaggerate it. Any questions for the 3rd physics? Adding the thermal stress and analyze the structural deformation. 1 second. So coming back to the slides. So far I hope I showed you the workflow where to find the different buttons. I mostly use the model builder because the ribbon was actually introduced later, so I'm more used to the older version of it. But hopefully so far I showed you how to solve a coupled phenomena, how to introduce the different couplings, and by now you understand there's no limitation to how many physics you can choose and what kind of coupling you can implement. Even for a single physics, it's a very useful or simple tool to have because you have the same workflow for all the physics that you also show, you also sort. And then I mentioned that anywhere you can type in constant, you can type in all the other different things, naming expressions, function calls. You can add user-defined equation. I haven't showed that yet. Oh, and parameterization. I want to quickly show that. It'll only take a minute or so. So a lot of times people want to compare different designs. Actually, let me disable this multi-physics node. It was introduced with the second set of equation I introduced. Thermal expansion, I'll disable that as well. Okay, so this was the working version of my last computation, the model. So what happens if I want to try a few different designs and see which one gives me the peak temperature, the highest peak temperature on one of the shoulder points? So what I'll do is, in geometry, I want to use a parameter to control that distance, extrusion distance, so the thickness of it. So just call it thickness. Of course, it's going to turn red because it's not defined anywhere. In global definitions, I can add parameter list, and here I'll say thickness 0.2. So, and then I can go to the study node, add a parametric sweep. So now here pops the entire list. Right now I only have 1 parameter. And I'll say instead of 0.2, run me 3 cases, 0.2, 0.3, and 0.4. Or you can use the range button right here, typing the beginning and what's the step. And now if I hit compute, it's essentially going to run the same problem 3 times with a different geometry. And every step is going to build a new geometry, build a new mesh, assemble a new system matrix, and then give me a solution. And it's going to put all the 3 solutions in one solution data set as 3 separate frames. So if I want to run an animation that loops through that 3 frames, I could actually do that. Of course, in time-dependent problems, you save the solution every certain seconds, and then you can run the animation of that as well. All right, so now you finish computing. So now you see, for example, if I look at the temperature plot, so I could choose a different parameter and hit the plot. It's going to update the visualization. And I said I want to look at the temperature information at the shoulder point. So let me first find out what's the coordinate of that shoulder point. I'm going to add a measure under geometry. I'm going to measure a point, 0.250.2. And then what I'll do is in the solution data set, so the solution we have saved so far, I'm going to right click, add a cut point 3D, type in 0.250.2, and choose that parametric solution. So I'm going to plot the information on that particular point. I'll add a derived value of point evaluation, use this data set, evaluate the temperature information. So now it shows me what's the thickness and what's that temperature on that particular point. I could run a graph, shows me where the highest temperature is. It shows up at the 0.4 case. Of course, it's only a small variance among the three cases. So what should we do? Run a mesh refinement study, right? Remember? So after then, you'll be confidently saying, which one actually gives me the highest temperature down.